Okay, thank you for the introduction, and thank you all for coming. So I'll be talking about joint work with Noga Alon and Colin Defont, who are both actually here right now. So if you have any pressing difficult questions during the talk, you put them in the chat, maybe they can answer, and I'm happy to answer all the easy questions. And I just want to mention also that Colin is presenting a poster this time tomorrow, and I encourage all of you to go check it out. So with no further ado, let me tell you what this Friends and Strangers Walking on Graphs thing is all about. So the setup is that we start with a simple graph, for instance, this graph here on 5 vertices. And then we start with some number of people, the same number of people as we have vertices on the graph. And we suppose that some of these people are friends with each other, and some of them are strangers. So here I've drawn an edge between two people if they're friends with each other, and I've not drawn an edge if they're strangers. So here I am in the middle, and here is Noga and Colin. And we all know each other. For instance, we wrote this paper together, so we're all connected by edges. And here's my friend Mehdi and my dog Maisie, and we all know each other also, so we're all connected by edges. But Mehdi and Maisie do not know Noga and Colin, so they're not connected by edges. So we have the second graph over here, which I'll call the friendship graph, which encodes who knows whom. Now we suppose that these people stand on the graph, one person on each vertex, like this. And they're allowed to walk around on the graph according to the following rule. If you have two people who are friends with each other and who are standing on adjacent vertices of the graph, then they can walk across the edge between them and swap positions. And we call this a friendly swap. So for instance, here's Colin and Noga, and they're standing on adjacent vertices of our graph on the left. And you can see that they're friends with each other because they're adjacent in this friendship graph, so they can swap positions like this. So I can show that one more time. So they start here, and then they swap positions. Likewise, I'm standing here next to my dog Maisie, and we're friends with each other in this graph over here on the right, so we can also swap positions. Now here we've got Mehdi and Colin, and they're standing on adjacent vertices of the graph over here, but they're not friends with each other, so they're not allowed to swap. However, here's another sequence of swaps that we would be allowed to do, and this just shows something kind of neat. So I'm friends with everybody, so I can swap with anybody I'm adjacent to. So for instance, I could swap with Mehdi, and then with Colin, and then with Mehdi again. And this sequence of 3 swaps has the overall effect of exchanging the positions of Colin and Mehdi, even though they were not allowed to swap before. So I can show you that one more time. So we started out with this configuration, and then after we applied these 3 friendly swaps, we arrived at this new configuration. Okay, so when you're given a graph, like this 5-vertex graph on the left, and some set of people, you can put them on the graph, and you can ask from which configurations of people standing on the graph can you reach which other configurations, using these sequences of friendly swaps. And in particular, when is it the case, for which sets of people in which graphs, when is it the case that you can get from any configuration to any other configuration? So these are the types of questions we'll be looking at in this talk. Okay, so now I'll formalize this notion. And this is the key new definition. So we're given n vertex graphs, x and y. We think of x as the graph that's being walked on, and y is the graph that encodes friendships. And then we define the friends and strangers graph, fs of xy, to be the graph whose vertex set is the set of all bijections sigma from the vertex set of x to the vertex set of y. So this is just the different configurations of people standing on the graph. So sigma tells you who's standing on each vertex. And then we say that 2 such bijections are adjacent in the friends and strangers graph if one can be obtained from another by a friendly swap. And so the connected components of this graph, for instance, correspond to equivalence classes of mutually reachable configurations of people under these friendly swaps. And here's a quick example. If x is this 5-vertex cycle graph and y is this graph here, then the friends and strangers graph looks like this. So you can see there's a lot of symmetry and a lot of structure going on. We have 5 isomorphic connected components, each of which has a lot of internal symmetry. And actually, we'll see later in the talk why there should be 5 connected components here, and this comes sort of from the fact that this graph x is a cycle. Okay, so let me just tell you why this is, or let me give you some more motivation for studying these things. So the idea is that it generalized a lot of previous work. So the first thing is that the friends and strangers graph of x with a complete graph Kn is the Cayley graph of the symmetric group generated by transpositions corresponding to the edges in x. So you can think of the vertex set of x as 1 through n, and if vertices I and j are connected by an edge, then we have that transposition. So this is something that's been studied. in a slightly more recreational tone, you can look at this 15 puzzle. So here you're given this grid, 4x4 grid, with tiles numbered 1 through 15. And there's a blank space, and you can slide a tile into the blank space. So the puzzle is, if you start with one configuration of these tiles, when can you reach another configuration? So this is equivalent to analyzing the friends and strangers graph of a 4x4 grid graph, this is what's being walked on, and this 16 vertex star graph. So here, the 15 leaves of the star correspond to the tiles, and the center of the star corresponds to this blank space, because any tile can move into a blank space, or swap with the blank space, but two tiles cannot swap with each other. So this is another example of a friends and strangers graph. So in the 1970s, not using this language of friends and strangers graphs, Wilson studied a generalization of the 15 puzzle, where he looks at essentially the connected components of the friends and strangers graph of an arbitrary graph X with an n-vertex star graph. So this is replacing the grid graph with an arbitrary graph X. And also, again, not using this language of friends and strangers graphs, Stanley studied the connected components of the friends and strangers graph of a path with itself, and this is related to multiplicity-free flag H vectors. So all of these things are examples of friends and strangers graphs, so let's see what we can say about them. So any questions before I continue? Okay. So I'll start with some basic properties of these friends and strangers graphs just to get a better feel for the objects. So for this slide, we'll let x and y be n-vertex graphs. The first thing to note is that isolated vertices in the friends and strangers graph of x and y correspond to edge disjoint packings of x and y in the complete graph Kn. And this is just unpacking definitions. So recall that an edge in the friends and strangers graph corresponds to a friendly swap that can be performed between two configurations of people. So a vertex in the friends and strangers graph is isolated if and only if there are no friendly swaps from that configuration. And this just means that whenever you have an edge in the graph X, the two people who are standing on those endpoints are not friends in the graph Y. So this is just a definition. Another useful fact is that the friends and strangers graph of x and y is isomorphic to the friends and strangers graph of y with x. So you can just think of vertices standing on people instead of people standing on vertices. And an explicit isomorphism between these graphs would send each bijection sigma on the left-hand side to its inverse. So we'll often state results in what looks like an asymmetrical way, but because of this fact, it's perfectly general. So for instance, one can show that if x is disconnected, then the friends and strangers graph of x and y is guaranteed to be disconnected for any y. And this is just because if x has multiple connected components, and somebody starts out standing on one of them, well, they can never walk over to another connected component. So there will be other configurations of people that cannot be reached. And then because of the second bullet point, if y is disconnected, this also forces the friends and strangers graph to be disconnected. Okay, so what else can force the friends and strangers graph to be disconnected? It turns out that if x and y each have a cut vertex, and the number of vertices is at least 3, then the friends and strangers graph is disconnected. And this is just a slightly harder version of this third bullet point. In another direction, if x and y are both bipartite, and the number of vertices is at least 3, then the friends and strangers graph is also disconnected. And the reason for this is essentially you can cook up an invariant modulo 2 for these various configurations and show that both values of this invariant can be attained. And the idea is that if we think of x and y as having vertex set 1 through n, then a bijection is actually a permutation, and we can look at the sign of the permutation. And then there's a little bit more, which I won't go into the details of. So these are a few things that can make the friends and strangers graph disconnected. And this brings us to the first result of Wilson that I mentioned before. So he's going to look at the friends and strangers graph of x with a star and ask, when is this connected? So we know from the previous few bullet points many things that make this graph not connected. And Wilson's result basically says these are the only obstructions. So suppose x is a biconnected, non-bipartite graph on at least 3 vertices. So this is sort of the obvious necessary conditions from the previous few bullet points. And then suppose further that x is not this particular exceptional graph theta naught, and that it's not a cycle graph on 4 or more vertices. So if x is not any of these problematic things, then we're guaranteed that the friends and strangers graph of x with a star will be connected. And the proof is pretty involved. And a nice thing is that we'll be using this theorem more later in the talk. Okay. So now I want to talk about other specific choices of the graph y. So we're going to fix y first to be a path, and we're going to ask what we can say about the friends and strangers graph of x with a path. So here's our main result. So we have our graph x, and we look at the set of acyclic orientations of the complement of X. And then we claim, or our result, is that there's a bijection from the set of acyclic orientations to the connected components of our friends and strangers graph of X with a path. And the vertices in one of these connected components are precisely the linear extensions of our acyclic orientation. So I should mention here, we're thinking of path as being on the vertex set 1 through n, where we have edges 1, 2, 2, 3, 3, 4, and so on. So let me just illustrate this with an example. So we can suppose that X is, say, this 3-vertex graph here. So then the complement of X just has this single edge down here, and there are 2 acyclic orientations. We can orient this edge in X bar from left to right or from right to left. And if you're given a labeling of the graph X with 1 through n, so this is just a configuration of the people, you think of orienting each edge in X bar from the smaller label to the larger label. And these would be sort of the linear extensions of an acyclic orientation. So here I've drawn the friends and strangers graph of X with path, and you can see it has 2 connected components. This top connected component corresponds to the acyclic orientation of X bar, where the edge is oriented from left to right. So here we have all the labelings where the label on the left is smaller than the label on the right. And then down here we have the other connected component, which corresponds to where you oriented the edge of X bar from right to left. And here you have the smaller label on the right and the bigger label on the left. And I think I'll just briefly mention why this theorem holds. So the first thing you have to show is that if you have a labeling of your graph X, and then you apply a friendly swap, this preserves the acyclic orientation. And this is because whenever you're applying a friendly swap, you're swapping the people with labels I and I plus 1. And the vertices that they're standing on had to be adjacent in X, which means those vertices were non-adjacent in X bar. And this means that when you swap the positions of I and I plus 1, this doesn't change the orientation of any of the edges in X bar. So the underlying acyclic orientation is preserved under friendly swaps. And then the other half of the theorem is showing that if you have 2 linear extensions of the same acyclic orientation, then you can get from one to the other by a sequence of friendly swaps. And this is just induction on the number n of vertices. So that's a very quick sketch of the proof. And I'll mention also that this is essentially equivalent to a known result about Coxeter elements in Coxeter groups, although the reduction, or rather the translation into that language, is at least as much work as the direct proof that I just mentioned. So this is more or less equivalent to known results. But the next thing I want to talk about is what happens if you replace path with a cycle. So we think of the cycle as being a path with the additional edge n1. So what we're going to get is sort of a toric analog of this theorem here, which I said is related to Coxeter theorem. Okay. So before I can precisely state this result about cycles, I need to introduce some notions of flipping. So if we're given an acyclic orientation of a graph G, we say that a flip is an operation which changes a sink to a source or vice versa. So for instance, this vertex here is a source because all the edges are oriented away from it, and we can flip it to turn it into a sink. Likewise, we could turn this vertex, flip this from a source to a sink, or this one from a source to a sink. So that's what I mean by a flip. And this is sort of well studied. What's new is this notion of a double flip. So to make a double flip, you choose a sink and a source that are not adjacent, and you simultaneously flip both of them. And then we can define this notion of flip equivalence and double flip equivalence on acyclic orientations if you can get from one acyclic orientation to another by a sequence of flips or respectively double flips. So these flip equivalence classes of acyclic orientations are also known as toric acyclic orientations and are pretty well studied, but these double flip equivalence classes are new. And now I can state our theorem, which tells us about the connected components of the friends and strangers graph of X with a cycle. So before I read the theorem, I just want to motivate this a little bit. So recall that cycle sub n is the path with an extra edge n to 1. And so we know that so we know that each connected component of this friends and strangers graph of X with a cycle will be a union of connected components of the friends and strangers graph of X with a path. Because if you can get from one labeling to another, one configuration to another, using just the edges from the path, well, you can certainly do it with the extra edge that you have in cycle. So the question just becomes when can you get from one acyclic orientation to another using this extra edge between person n and person 1. Okay, well, let's think about this a little bit. So let's say that we have a friendly swap involving people 1 and n. So person 1 must have been standing on a source, because that person's the smallest label, and person n must have been standing on a sink, because that's the biggest label. And if they're able to perform a friendly swap, this means they must have been standing on adjacent vertices in X, and so they were standing on non-adjacent vertices in X bar. And then you can see that when we apply this friendly swap, this is precisely applying a double flip to the underlying acyclic orientation of X bar. So that wasn't quite a proof, but you can make it a proof, and this gives that there's a bijection from the set of double flip equivalence classes of the acyclic orientations of X bar to the set of connected components of our friends and strangers graph of X with a cycle. And the vertices in such a connected component are precisely the linear extensions of the acyclic orientations in this double flip equivalence class. So this is our toric analog of what we saw in the previous slide, but it's not very helpful unless we can actually say something about these double flip equivalence classes. So that's the next order of business. So now the goal is to relate double flip equivalence classes, which we're interested in, to flip equivalence classes, which are well understood. And our main theorem, which is really the hardest part, is the following. So let nu be the GCD of the sizes of the connected components of a graph G. And each flip equivalence class of acyclic orientations of G is a union of exactly nu double flip equivalence classes of acyclic orientations of G. So I'll just illustrate this with two examples. The first one here is where G is this triangle, and I've drawn the double flip equivalence classes in blue. These are all singletons. And I've drawn the flip equivalence classes in red. So you can see, sure enough, nu equals 3, because there's one connected component of size 3, and each of the flip equivalence classes splits into 3 double flip equivalence classes. Here's a slightly bigger example. Here again, we have only one connected component of our graph G, and it has 5 vertices, so nu equals 5. So here there's only one flip equivalence class outlined in red, and then we have 5 double flip equivalence classes outlined in blue. So note that there are different sizes in this case, but the point is that there's 5 of these double flip equivalence classes. And I'll mention that the proof of this theorem really relies on thinking about these friends and strangers graphs, even though this theorem looks like it's a statement just about acyclic orientations. Okay, so if I can return to what this says about our cycles, the idea is that we can use known results about flip equivalence classes. So we get the following corollary, which is that the number of connected components of the friends and strangers graph of X in cycle, which is precisely the number of double flip equivalence classes, is nu times the evaluation of this Tut polynomial of X bar at 1, 0, where nu is again the GCD of the sizes of the connected components of X bar. And this is just using the fact that this evaluation of the Tut polynomial counts flip equivalence classes. And then we can specialize this to say that the friends and strangers graph of X with a cycle is connected if and only if X bar is a forest with trees of relatively prime sizes. And this is just because we need nu and this polynomial to be equal to 1. So this is a pretty satisfying answer to when we can have, for which graphs X give us a connected friends and strangers graph. And recall that this condition corresponds to the situation where you can get from any arrangement of people to any other arrangement of people using friendly swaps. Okay, so that's all I want to say about paths and cycles. And for the rest of the talk, I'm going to very quickly survey some other results. And my goal is just to show you how many different types of questions you can ask about these friends and strangers graphs. So one natural thing is to ask about minimum degree conditions that guarantee a connected friends and strangers graph. So more precisely, what's the smallest value dn, such that if x and y are n vertex graphs with minimum degree at least dn, you're guaranteed to have the friends and strangers graph connected. So Noga, Colin, and I got some bounds on this. We showed that this is between around 3/5 n and 9/14 n. And the lower bound is a construction, and the upper bound is a pretty complicated proof. But recently, this was improved a lot by Kirill Mangachev, and he showed that we actually have an upper bound of ceiling of 3/5 n. So now we know what dn is up to plus or minus 2 or something. So this is a very nice result, and he actually, in proving this theorem, settles many cases of the asymmetric version of the problem, where you impose different minimum degree requirements on x and y, and ask which pairs of minimum degree requirements guarantee a connected friends and strangers graph. So this is one direction you can go in. Another is you can look at the case where x and y are random graphs. So suppose that x and y are independently chosen Erdős-Renyi random graphs with n vertices and edge probability p. So the first half of this theorem says that if p is smaller than around n to the minus a half, then with high probability, the friends and strangers graph will be disconnected. And the second half of the theorem says that if p is bigger than some subpolynomial factor times n to the minus a half, then with high probability, the friends and strangers graph is connected. So the first half of this theorem is pretty quick to prove. And one nice thing is that it actually shows that with high probability, the friends and strangers graph has isolated vertices, which kind of suggests that generically, the main obstruction to having a connected friends and strangers graph would be isolated vertices. The second half of the theorem is much harder to prove and much more elaborate. The one thing I'll say is that it uses Wilson's result about the friends and strangers graph of x with a star many, many times in the proof. So it's sort of nice that that ends up being useful. And the main takeaway from this whole theorem is that the threshold, the edge density threshold for going from disconnected friends and strangers graph with high probability to connected is right around n to the minus a half. Okay. So I want to mention briefly some more recent results. So Ryan John recently resolved two of our open problems. The first thing that he showed is that if the friends and strangers graph of x with a cycle is connected, then the friends and strangers graph of x and y is connected for every biconnected graph y. This is sort of natural. You can ask, okay, what are the graphs x such that the friends and strangers graph of x and y is connected for every biconnected graph y? Well, cycle is kind of the minimal biconnected graph, if you think about like an ear decomposition or something like that. And so this shows that among all graphs y, all biconnected graphs y, the one which makes it hardest for the friends and strangers graph of x and y to be connected is precisely the cycle. And I'll mention also that we know from our previous work on cycles exactly which graphs x satisfy this hypothesis. Okay, and Ryan proved one more result, which is that there exist graphs x and y such that their friends and strangers graphs have components whose diameters grow super polynomially in the number of vertices. This is somewhat surprising, and the construction of the families of graphs is quite elaborate. So I just wanted to mention this result as well. And I want to conclude with a couple of open problems. So the first one is looking at more general flip equivalence relations. So if I give you a pair AB, you can think of defining an AB flip as on an acyclic orientation as taking A sources and B sinks and simultaneously flipping all of them. So we kind of looked at our normal flips were 0-1 flips and 1-0 flips, and then our double flips were 1-1 flips. And so we were able to relate the 1-1 flip equivalence classes with these other single flip equivalence classes. And it might be interesting to relate the AB flip equivalence classes for various values of A and B. Something else would be characterizing the edge subgraphs y of the complete bipartite graph KRR such that the friends and strangers graph of KRR with y has exactly two connected components. So this friends and strangers graph will be guaranteed to have at least two connected components because both y and KRR would be bipartite, and this was from the fact I mentioned at the very beginning. So then this is sort of a very natural question. It's how can you, which graphs y make this friends and strangers graph have as few components as possible? So in general, for many of the results that I mentioned, there's a bipartite analog where the goal is to have only two connected components instead of only one connected component in the non-bipartite case. I'll mention as a third open problem to finish the work of Bogachev. So here we're going to look at x and y having different minimum degree conditions and asking which pairs of minimum degree conditions guarantee a connected friends and strangers graph. So he resolved a lot of cases of this problem, but there are still a few open cases, and it would be interesting to solve the remaining ones. And finally, I want to pose as a very vague idea for future work, what can we say about friends and strangers randomly walking on graphs? So that's all I have, and I thank you for listening with this little graphic.
Thank you. Perfect timing. A nice picture. Questions, anyone? So we already had a few questions that were answered by your co-authors, so that was very handy to have them around. I see one more question by Rani Hod.
does it make sense to ask about the friends and strangers graph of x and x for x the same random graph? Yeah, it certainly makes sense. I don't think we can say anything about that using our results, but certainly you could ask it. That's not much of an answer, I know.
More questions?
I had a question. So there's this nice result. If both graphs are disconnected, then it's friends, strangers. Sorry, both graphs are bipartite, then it's friends, strangers graph is disconnected. Can you say if both graphs are, say, tripartite, can you give some sort of bound on the connectivity? So say it might be connected, but how connected is it?
I don't know. I sort of expect these graphs to be, these friends and strangers graphs to be pretty highly connected, because often there are a lot of sort of disjoint friendly swaps you can do. You could do a friendly swap over here, and then you could do another one over here, and then you could sort of keep going where you were before.
Yeah, it might be nice to quantify that.
Yeah,
Say what you can say about the in general, what is the connectivity of these graphs?
Yeah, for sure. I have no idea.
Other questions? Yes, one question from Elias.
Okay.
In the chat.
15 puzzle, sorry, depends on the parity of some parameter. Can this be proved or detected? So, okay, let me go way back to this slide. The answer is yes, I guess. So we're looking at this friends and strangers graph of this grid graph with a star. And both of these graphs are bipartite. So you know there's going to be at least two connected components of the friends and strangers graph. And so this result of Wilson is actually even a little bit stronger than what I mentioned. It also shows that in cases like this, we have only two connected components. So we have this invariant modulo 2 that I mentioned for bijections that are going to be in the same component of the friends and strangers graph. And this result of Wilson tells us that if you have two bijections with the same value of this invariant, then they are guaranteed to be in the same connected component of the friends and strangers graph. So to answer the question, if there's not a parity obstruction to getting from one arrangement to another in the 15 puzzle, then you can indeed get from one to the other.
All right, thank you very much. You can ask more questions in the chat that Noah can answer later, but we are now going to switch to the next speaker. Thanks again, Noah. That was a very nice talk.